Hello, hello, hello. Welcome back. It is Thursday, the 7th of May. Weird for me to be streaming on a Thursday, but it's the time I had, so it's the time I'll take. And it's important that I do because we've only got 2 weeks left until the start of A-level physics. And today I'm going to be going through circular motion and simple harmonic motion to help bridge that gap with some of the few remaining topics I haven't been through. I know I haven't covered... What have I not covered? I've not done electricity, and I've not done forces, motion, and energy. So as always, let me know if there are certain topics you guys really want me to cover, and I'll make sure to get those done in time. But today I thought it would be good to go through the circular motion and the simple harmonic motion, because there are just some little bits in there that I think some people always have issue with. Now, I'm going to try and get this done in an hour to give me time to get out and vote. Because today is voting day, and I do want to make the most of that. But it's been very busy, and I haven't quite got around to it. But I'm going to try and get that done, which means we are going to race through this. So without further ado, always is, by the way, in the chat, drop a comment. Let me know if I've explained something too quickly or if you want me to go through a different case study. I've got some notes to go through, so hopefully I cover everything. But always, I'll be keeping an eye on the chat, answering some questions as usual. So without further ado, let us get into it. So starting the screen share. First thing to say about circular motion. Well, actually, let's have a little conversation about it first. So first thing to note about circular motion. Obviously, no points for this. It's moving in a circle. But the main thing here is about the centripetal force. The fact that there is a resultant force acting towards the center of the circle, which is acting at right angles to the velocity. Now, importantly, this is a sort of application of Newton's first and second laws, and they do like to ask about that. So, for instance, we know that Newton's first law tells us that if there was no force zoom in. If there was no force acting on an object, then it would just be moving in a straight line. If there is a resultant force acting on the object, that is going to cause the object's motion to deflect. That is going to cause an acceleration, so a change in the velocity vector. So for instance, if this is just an f bigger than 0, but not equal to mv squared over r, we will get it to deflect. This might be the case, for instance, when you have a charged particle between parallel plates, it will just sort of move in a parabola. In the very specific instance where f equals mv squared over r, then, and only then, why am I streaming? Because I like it. mv squared over r. So I think the reason why I'm streaming is it's kind of like me giving a free tutoring session to the internet. Like if you had a test on this topic tomorrow, what are the most important points you would need to know? So if and only if f equals mv squared over r, then you get circular motion. Why am I streaming with 3 viewers? Because it doesn't matter that I got 3 viewers. This is about sort of me improving my ability to communicate my ideas and kind of teach on my own, as opposed to just reacting to a student that's in front of me. Plus, I like it, so why not? Okay, so if f equals mv squared over r, then it will move in a circle. If the resultant force is anything other than mv squared over r, then circular motion cannot be maintained, and it will not move in a circle anymore. So, because the reason why is because of Newton's first law, right? If anything sort of left on its own would want to move in a straight line. So the reason why they like this explanation, right? Because it's changing direction, the velocity vector is changing. Because the velocity vector is changing, we know it's accelerating, which means we know there's a resultant force. That resultant force is perpendicular to the velocity vector, acting towards the center of the circle, and then you get centripetal force causing circular motion. Importantly, because that force is perpendicular to the velocity vector, that means that there is no work done. Because remember that work done is the distance, is the force times the distance moved in the direction of the force. And because these are perpendicular, you get no work done, right? And we know that because that means it's moving with constant speed in a circle. And if F were to be bigger than mv squared over r, you would get some sort of spiral motion. So a lot of circular motion is to do with working out what that resultant force is towards the center of the circle, and therefore equating that to mv squared over r. But remember that if F, the resultant force, is ever not mv squared over r, then it stops. So another question is, where does this equation come from? Because I have seen them ask you to derive the centripetal acceleration. So here, if we have a sort of circle, so let's consider it in sort of two positions where this is obviously and completely the center of the circle because I am so good at drawing. But let's say it moves through this small angle, delta theta, right? And that's radius r. Then we know here, the velocity, we'll call that VA. The velocities are going to be tangential to the circle, right? So we can draw on the side, that is VA, and that is VB. And this is the change in that velocity vector, which is sort of straight down, where this would also be delta theta. Now, the point here is that if delta theta is small, then this distance along the circle delta S will be approximately linear. And we can say that approximately speaking, delta S over R will equal delta V over V. Now, that delta S, we know, is going to be the same as speed times the change in time. That is how far the distance is moved along the circle. So if we sub that in and we rearrange, we get that v squared over r equals delta v over delta t, which is the acceleration. And that is the derivation of the centripetal acceleration for circular motion. Not often understood, sometimes examined, very worth going over. Now, this does assume a sort of understanding, by the way, of centripetal, or sort of rather angular momentum. Not angular momentum, angular velocity. So we can also say that omega is the angle moved through in sort of unit time. So for instance, in one complete circle, it does an angle of 2 pi in a time of big T. And that omega is very important in circular motion. Now, let me think. Are there things that I want to go through? Yes, there are. Please pause while I find those. Yeah. So let's consider as well the speed of things moving in a circle. So if we draw a circle at any one point here, the speed v is going to be equal to the distance traveled over the time taken. So for instance here, if we consider one complete rotation, then the distance traveled around the circle would be the circumference of the circle, which would be 2 pi r. And the time taken would be delta t, or rather would be big T, the time period for circular motion. And then if we see this 2 pi over t here, that is omega. So we can also say that v is equal to omega r. And so these relationships are very helpful in certain questions. So for instance, a common question type, which kind of trips people up from my experience, is if they're talking about sort of revolutions per minute, for instance. So let's say we had something, let's say we needed to, so something has a mass of 10 kilograms and it's going round in a circle of radius 0.8 meters and it's going at like 200 RPM. That's revolutions per minute. What you would need to do in this sort of situation is to work out the revolutions per second, because in physics, we're always working in a base unit of seconds. So if there are 200 revolutions in 60 seconds, then there are 200 over 60 revolutions per second. Now, I have left my good calculator in the other room, so I'm going to have to use, a bad calculator. But that is A-okay. So that obviously simplifies to 10 over 3. That is the number of revolutions per second. That is the frequency. And so we can also say, by the way, that omega equals 2 pi f. So therefore, that would be 20 over 3 pi. From this, we could also say that V would be equal to omega r. So 20 over 3 pi times 0.8, which is 16 over 3 pi meters per second. And we could work out the centripetal force required and say that F equals mv squared over r, which we can put in the numbers and get a nice value for that centripetal force required. So it's 10 times that thing squared all over a radius of 0.8. So if I plug that in, I get an answer of, well, how do I, guys, I'm so bad at pressing the buttons. Where's the pi on this calculator? God damn. There it is. Sorry, it's the new class whiz. It's just bad. I like the old class whiz. All right, so 16 over 3. Ugh. It's all right, guys. Next time I'll make sure I have my good calculator. So that thing squared. In fact, what I really should do is I should get my calculator out on the screen, but I haven't, and that's fine. So 3509 newtons, sort of 4 sig figs there, nearest Newton. So these kinds of calculations, if you ever see RPM, the idea is to convert that into a frequency, which you can plug in to work out things like V and omega. So now, having gone through the derivation of the centripetal acceleration, let's go through some of the specific examples they like you to work with. So for instance, the horizontal circle, this is something like on a road. This is where you don't consider gravity. This is not a vertical circle. Let's consider some of the sort of road physics. So for instance, in the case where we're going over a hill, say, what you always want to do is to draw on the forces. So there's some reaction force acting up. There's some, someone saying, quite sure this will reach JEE advanced aspirants. Possibly. If you think it's helpful, we can make it spread. You guys know how to work the YouTube things. So here, if we have our car on the top of a hill, and we know it is moving with speed v, we know at this point, at the top of the hill, it is moving in a circle, roughly, if that's how we're modeling this. In this case, remember that F equals mv squared over r. And the question you always ask yourself in circular motion is, what is this resultant force? Because this F in F equals mv squared over r is a resultant force acting towards the center of the circle. In this case, knowing that the center of the circle is acting downwards, so that will be my positive direction, my resultant force is going to be mg minus r. And so a typical question might be, what is the maximum speed you could travel before the car loses contact with the road? Because we know if you're going over a hill too quickly, you'll eventually kind of go airborne. And so what you can do is to rearrange this for R. Or rather, what you can say is at the point at which the car is about to go airborne, the reaction force will go to 0. And so you will just get that mg equals mv max squared over r. And you end up getting that v max is the square root of rg. So that would be one way of working with that. Another application on roads is to consider motion on a roundabout. Now, if we're considering a roundabout, and this is your car, the weight would be acting into the plane of the paper. The reaction force would be acting out of the plane of the paper. You would have a driving force operating forwards, but the force acting towards the center would be the friction. And that would be the only force acting towards the center. So in this case, when we're considering F equals mv squared over r, this resultant force will be the friction. And in the case of limiting friction before it starts to slip or flip or do some other nonsense, that would be equal to mu times the reaction force. Mu r would equal mv squared over r. And the reaction force would be equal to the weight on a road. So that would be mu mg equals mv squared over r, where you can cancel the m's and again get that v max, which would be the square root of mu gr. So a lot of these questions, yes, they get you to derive the general expression, but a lot of times they're looking for this maximum speed before something weird happens, and it transitions out of circular motion. My personal favorite of these, by the way, is the banked slope, or the banked track. So if we have something moving on a bank without slipping, I'm going to model it as a particle. You sometimes see it as a proper car. Mu equals tan theta. Oh, here we go. He's ahead of the curve. It's a slight variant on that. What we're going to have here, though, so I'm not going to consider the case where we consider the two separate wheels. I'm just going to consider this, for this purposes of this stream, as a particle. I'm going to call it mg down. I'm going to say there's a reaction force. I'm going to say, let's consider what would need to happen for it to move in circular motion without friction. Because that's often what they're asking for on a bank track, is for frictionless motion. If you wanted to make this more difficult, we could consider what would happen with friction, but for now, we're just going to consider it without friction. So here, we're going to, again, go for our F equals mv squared over r. We're here, as always, we need to ask ourselves, what is this reaction force? Not the reaction force. What is the resultant force acting towards the center of the circle? So in this case, this angle here would be theta, and this angle here would be theta. Theta, is that right? 90 minus theta, theta, 90 minus theta. Yes, theta. So what we would say is that r sine theta, to open that angle up, would be equal to mv squared over r. And we know that r cos theta would equal mg. So what we can do is to divide these through, and we get tan theta is not equal to mu in this instance. It would be equal to v squared over gr. And we would get that v is equal to the root of gr tan theta, where this would be the perfect speed in order to ensure frictionless motion on the banked track. difficult case study if it comes up. What they could also ask, by the way, is what would happen if the speed increases? Which way would friction be acting? Because this is the perfect speed for no friction. But then you need to consider, so like as if v increases, then obviously mv squared over r will increase, which means the resultant force acting towards the center of the circle will increase, which means that the friction must act towards the center of the circle. So if the friction is acting towards the center of the circle, it is opposing attempted motion. So it would be attempting to move up the ramp away from the center of the circle. And that's how you can kind of piece these things through logically, one step in front of the other. By the same reverse logic, if the speed were to decrease, this mv squared over r would decrease, the resultant force would decrease, and you would have friction acting up the slope to stop it slipping down. In terms of the applications, we also have more of these vertical circles, which are my personal favorite. So let's consider, for instance, a sort of roller coaster where you're at the bottom. In this case, there's the reaction force acting upwards and the weight acting downwards. And we can say that R minus mg, which is the resultant force acting up towards the center of the circle, equals mv squared over r. Nice and standard. More complicated is something where they get you to drop, right? So let's say something is up here, it then swings down, and it wants you to work out the tension at the bottom, say. So what we would say here is that if this is radius r, we can see that it has dropped through a vertical distance of r from where it started. So the loss in GPE is going to equal the gain in kinetic. So the loss in GPE will equal to mgr, which will equal the half mv squared. And this will allow us to work out what that v squared is 2gr. That is the v squared we can put into mv squared over r. Where in this case, if we think about it, the center of the circle is up here. So the resultant force must be acting upwards. So therefore, it must be T minus mg, where the positive direction is in the direction of the center of the circle. And that will equal to m v squared over r. Does this apply to EdXL? Some of these individual cases may not apply to EdXL, but I think on the whole, the physics is the physics. I don't have as many people doing the specific EdXL physics board. Is that true? I think I might have one. I think it does apply to EdXL. I can look up the specifics of that. The individual cases may vary. But I would say the principles certainly apply to EdXL, even if the specific cases don't. So in this case, we can plug that in and get the tension equals 3 mg, which is quite cool. Okay, so is there a final case, or is that kind of it? Yeah, oh yeah, let's do a sort of the roller coaster. So another question might be, let's say we've got a roller coaster which does a loop-de-loop. And you need to work out, say, oh yeah, this is a classic. So yeah, I'll just So this could be a roller coaster. This could also be, for instance, swinging a bucket of water around. And they could ask, like, how fast does it have to be moving at the top such that the water doesn't fall out? Or in the case of the roller coaster, how fast does it need to be moving so that you don't fall out of the roller coaster? So in this case, we have our radius again. At the top, we need to consider that we would have a reaction force acting down, and we would have the weight acting down. So both of those added together would be the resultant force equaling mv squared over r. And in the limiting case, that reaction force will go to 0. This will be the minimum speed, which causes this to be its minimum when r is 0. So mg equals m times v min squared over r. And we get that v min squared is equal to, or v min is equal to the root of g times r, which is the minimum speed it must have at the top of this loop in order to keep going in circular motion and have the people on the roller coaster not fall off, which is typically ideal. This exact scenario, by the way, would work for something tension. The general case for illustration of vertical circular motion, T equals mg. Yeah, exactly. I think the general case actually is, while true for, I would expect the general case to show up if you were doing further math mechanics. I wouldn't expect that general case to show up in doing just normal A-level physics, but it is good that you have that handy. This exact thing works, and by the way, you could take this one step further and say if that is the speed it has to have here, you can work out the kinetic energy there. So the kinetic energy at that point would be equal to a half mv squared, where v squared would be gr, so it would be a half mgr. And so you can work out the initial height that the roller coaster would have to drop from. Because that change in energy there, so what you would need to have is that this mg delta h here would need to equal the half mgr. So you can cancel that and say that this needs to be a half r, and the diameter of the circle is 2r, so the maximum height would have to be 2.5 r in order to keep it going. So there's lots of cool applications you can get with circular motion. So if you have a specific case study that they really like in your exam board, make sure you're prepared for that. But what I'm trying to demonstrate here is the general principles will always see you through. Where all you need to do is to first understand the story of the problem, how the circle is moving, where the direction of the center of the circle is, and it's always working out the resultant force in that direction and equating it to mv squared over r, understanding that limiting cases will be when the friction exceeds mu r, or when a reaction force or tension go to 0. So hopefully that kind of demonstrates a lot of these good applications of circular motion. If you have any specific questions, as always, feel free to drop them in the chat. But in the meantime, I'm going to quickly dip over into simple harmonic motion. Now, the most important thing about let's talk about the everyday cases of simple harmonic motion you know. We'll get onto these, but the ones you care about are the mass spring system and the small oscillations of a pendulum. So these are your just classic oscillations. This is something moving back and forth. Now, what are some of the key features of these oscillations? Well, we know that in both cases, there is some restoring force pulling it back towards this equilibrium position. So it goes away and then it swings back, overshoots the mark, and then swings back again, right? And as you get into the physics of it, you start to get in very important definitions. Where the first thing you need to know is that the definition of simple harmonic motion is that the acceleration is proportional to the negative displacement. Or in other words, So it's proportional to the displacement and in the opposite direction, which means it is always acting towards the equilibrium position. So that's the kind of corollary of this. You get a restoring force acting towards equilibrium. But this is the core definition. And what we can say, obviously, from your math, if it's proportion, I should not try and spell while I'm talking. If it's acting towards, if it's proportional, sorry, we know that that would give us an equation, a equals minus kx. And we can show that that constant of proportionality is omega squared. So this is another very important equation that shows up a lot in these sorts of questions. Now, how can we prove this? Well, what we know is with these oscillations, it's going to be sinusoidal in form. So we know that you're going to have a sort of cos motion for a displacement. So we can say that x is equal to, let's say, a for amplitude, cos omega t, where omega is that angular momentum. In case you're wondering why that should be the form of it, let's consider what happens here at the time period t, where it's completed one complete oscillation. We know that in that case, that is the equivalent of it moving through 2 pi radians in terms of a degree. So that would be like the cos graph moving through 2 pi, which is why it does one complete oscillation and ends up back at its start position. So we know that omega t would be equal to 2 pi, and that gets us our omega equals 2 pi over t as required, right? So that's why omega t gets us the results we need when t equals the time period. So that explains the form of this displacement graph. Then we know that v is dx dt. And for those of us, which is most of us, doing A-level math, you know how to differentiate this. This would become minus a omega sine omega t. And then the acceleration would be dv dt. And we can differentiate this again and get a omega squared cos omega t, which is equal to minus omega squared x. And so we can kind of derive it from there using this like first principles idea. I'll kind of leave it to you to work out what those graphs look like. Actually, no, I'll do it all. Let's draw the graphs. So if that is our displacement graph, then the velocity graph would be negative sine omega t. And the acceleration graph, nope. And the acceleration graph would be minus cos. And what that then shows us, by the way, so this would be at t over 4. If we could, let's put some specific times on. This would be t over 2. This would be 3t over 4. And this would be at time period t. And we can do the exact same thing with the other graphs to show these general results. T over 4, t over 2, 3t over 4, and t. And same thing here for this displacement graph. T over 4, t over 2. I keep on wanting to make that a pi. I'm so trained for math. Okay. And you can take these graphs and therefore understand what's happening in general in terms of energy. Because we can see here that when the displacement is 0, which is at the equilibrium position, we can see we have our maximum speed. And we would have acceleration is 0. So in other words, if we have, for instance, I'll demonstrate this with a pendulum. If we have this maximum displacement, if x is a maximum, then v is 0, and a is a maximum. If x is 0, then v is a maximum, and a is 0. And again, x is going to be max on this side, but in the negative direction. V would equal 0, and a would be a maximum. And we can use this idea to understand what's happening in terms of energy. Because we know that potential energy is proportional to x squared. So you could consider, for instance, a spring, where you know that the spring, the potential energy there would be a half kx squared. We know that if we consider energy against displacement, you would get a quadratic x squared curve. And because we know the conservation of energy, which tells us that energy cannot be created or destroyed, it can be simply converted from one form to another, we know that the potential energy that was a maximum here is all converted into kinetic energy by the time you get to the equilibrium position. In other words, the total of the potential and the kinetic energies will be a constant. And the kinetic energy will simply be that constant value minus whatever the potential energy is at that point. So if you were ever trying to work out the speed of a particle at any point in its simple harmonic motion, the way you would do that is to calculate the total energy, which would be equal to the potential energy at maximum displacement or the kinetic energy at equilibrium. That would give you the total energy. And then at your different displacement x, you would then work out the potential energy. And then the total energy minus that potential energy would give you the kinetic energy that's there. From there, you would work out half mv squared. So let me kind of put a bit more meat on the bones, and we'll kind of give you an example here. So this would be the amplitude A. So let's say, for instance, the amplitude was 10 centimeters. Let's say we had a spring constant. Oh, we have a question. What if I place a block over a body doing, at its extreme position, doing simple harmonic motion? I'm not sure what you mean by a block. I suppose if you, but if you ever stopped it, it would stop being simple harmonic motion, and then different physics would apply. Let's work out what would happen here. So we would know in this instance, for instance, the maximum potential, so the EP max would be equal to a half kx squared. So let's say that k was 10 newtons per meter. Yeah. The EP max would be a half times 10 times 0.1 squared, which would give me a value of, if I run that in my calculator real quick, 0.05 joules. Hello. That is therefore the same as the total energy. And if I wanted to work out the speed at, say, 5 centimeters, what I would do is to work out the potential energy at that point, which would be a half times 10 times 0.05 squared, which again, if I run that, I would get a value of 0.0125 joules. That would mean that I would get a kinetic energy, 0.05 total energy, minus the potential energy it has at that point. So 0. minus answer would be equal to 0.0375 joules. The JEE, I hear so much about this JEE Advance, and I've had a look at it, and I just went, nope. But what I would say, first of all, find any channels that are covering JEE Advanced specific. Second of all, find ways to demonstrate what you do understand from the syllabus. Typically, these really difficult problems can be simplified in some way such that your knowledge can be applied. And so what a lot of these specialists will teach you is how to break problems down into simpler chunks that make them solvable. So usually it's not about being smarter, it's about making the question dumber and much more able to answer. That is my top tip. And then finally, taking it back to here, now that we've worked out the kinetic energy, what you would do is therefore equate that half mv squared, and you could then work out the speed at that point. So that's how to go through these energy calculations using this general graph. And there's one final thing I want to point out, which is the maximum speed. So the maximum speed, we know here, so the total is a half k a squared for the amplitude. Well, that would be equal to half mv max squared. There's one other thing I have to go into before this is going to make sense. I'm going to come back to this. Because first we've got to derive what's happening for the specific cases of the mass spring system and the pendulum. Oh, someone asked, what's the minimum coefficient of friction to start pure rolling? Ooh, that is going to be beyond the scope of what I covered today, mainly because I've got to leave in 15 minutes, but I may come back to that another time if you check in. I'll have a look at that, because when you get into rolling, things start getting weird, because it's not just, the rotational mechanics is like beyond A level. Because I think as well, the friction doesn't act the way you think it's going to act. It's like a whole situation. I would say find someone smarter than me and ask them. But I will quickly, before going, let's do these derivations for the pendulum and the mass spring. So for a pendulum, let's say I've got this, and I'm displaced some angle theta, which is supposed to be small. I will make it look big so that we can actually tell what's happening. Let's think about the forces acting on this particle. So we know that T cos theta would equal mg, and we know that T sine theta would be the resultant force. So that would be the F, which is equal to ma, which is m omega squared x, where that x is the displacement, right? So what we know or rather, let's think about this differently. So we would know that the restoring force acting towards equilibrium position is equal to minus m. No, hold on a minute. No, I'm tongue-tying myself. I think I was right the first time. Look, let's just sort of make it simple. So we know that T sine theta is the resultant force, which is equal to ma. And we know that T cos theta is equal to mg. We can divide these through and say that tan theta is equal to a over g. So g tan theta is equal to the acceleration. We also know if small angles, then tan theta is approximately sine theta and therefore is equal to x over L. So therefore we have that gx over L is equal to A. But remember, A is equal to minus omega squared x. And because, well, I just should have put the negatives in for direction. And then what that basically gives us is that omega squared is equal to g over L. And remembering that, so that means that omega is equal to root g over L, which is 2 pi over t. So t is 2 pi over omega, which would be equal to 2 pi root L over g, which is the expression you have in your formula book. Are you live for real? Yes, I am live for real. Assuming that's what FR means. This is very, very real. This is ask a question and I will do my best to answer it. Yeah, I just tutor the internet for free. It's fun. So that is that. Then we also got the mass spring system, which is, so we've got like, I'm not going to do it vertically. I'm going to do it like horizontally. Nope, lies. That's not what a spring looks like. So let's draw spring, with a thing. You've got your circular motion test tomorrow. Woo! This is why we do it. Sorry you've caught me in the simple harmonic motion bit. But you can always, like, as soon as I stop this, it's going to go up on YouTube. You can go back for the circular motion bit. Drop a comment in chat if there's a specific thing you want to go through, and I can tell you if I covered it or not. If I didn't cover it, I can make sure we get this covered. Okay, so let's say this is the equilibrium position. This would be x. We know that there would be a force here. And we know that the force would be F equals minus kx, which is equal to ma. This is much simpler, right? So then minus k over mx equals a. But reminding ourselves that a was equal to minus omega squared x, it means that omega squared is equal to k over m. And we go through exactly the same thing for the rest of it. Omega is root k over m, which is 2 pi over t. So t equals 2 pi root m over k. Okay. Now, the reason why I said we had to do this and then come back is if we consider over here, the best case to really understand this is to think about the mass spring system, because that's kind of perfect. That doesn't rely on small angle approximations or other weird things. There's a topic in circular motion relating kinetic energy and potential energy. We did that. So you'll want to look at the fairground rides, the vertical circular motion that I covered. I covered like a sort of swinging down and what the tension of the string would be at the bottom. I also covered the case of the roller coaster and how fast it needs to be moving at the top to stop people falling out. Water slide, yeah, that kind of thing. The basic idea is to convert GP into kinetic energy. That gives you the V squared that you plug into F equals mv squared over R. And you need to remember that your resultant force is acting towards the center of a circle. Yes. So they're all very common applications. So definitely go back and check that out. I did a couple of cases of the sort of loop slide water thing. So here, we know that, so it was true that here the EP max is equal to a half Ka squared, which was equal to a half mv max squared. So canceling these, we know that V max, I can't spell, I'm just totally illiterate. So V max squared equals K over MA squared. But we see that this K over M is equal to omega squared for the mass spring system that we're using to model this energy. So therefore, it's equal to omega squared A squared, and we get this very overlooked equation that V max equals omega times the amplitude. And I really recommend you guys hold on to that one because it is a sneaky one that they like to slip in there. Am I looking? I'm going to look and see if there are any interesting questions here. No, I'm going to carry on because I want to cover damping and resonance quickly before I go. Where everything we've discussed so far about simple harmonic motion has been perfect simple harmonic motion, where it would go on forever, all of the energy stays total, none of the energy is lost to the surroundings. But as we know, if we let a pendulum go, it will eventually come to a rest. And that is because of the damping. So I'm going to remind you about light, critical, and heavy damping. Well, first of all, damping is due to energy being lost from the system. So the oscillations lose amplitude over time. So this would happen, for instance, if you had friction or if you were moving through a fluid with resistance. So air resistance or fluid resistance, something like that, taking some of the energy away. So light damping, you would still get oscillations happening with the same frequency as before, but the amplitude of the oscillations would decrease over time. So that would be your light damping situation. Your critical damping situation is where it comes back to equilibrium as quickly as possible and then stops. So that would look like, in this case, it would basically go as quickly as before and then just stop, where this time would be exactly the same as this time. Where that's not, I'm not going to call that big T because that's not the full time period, but which reminds me, I have to go back and do something. You are very welcome. Good luck with your test, sir. So this would be critical damping, where it comes back to equilibrium, basically just stops dead. And then your heavy damping would come back very, very slowly. So as opposed to critical damping, which gets you back to zero, maybe overshoots a tiny bit, but you basically just stop the oscillations dead immediately. Your heavy damping creates so much resistance that you're only slowly able to return to equilibrium, like this, where it sort of does exponential decay and very slowly returns to equilibrium. So the applications of critical damping would be, for instance, car suspension, where you want the oscillations to stop as quickly as possible. I will go back because I've just remembered one trap when we're considering simple harmonic motion that a lot of people fall for. So I want to show you, this is the energy against displacement curve, but the energy against time curve is so important. So if I show you here, in one oscillation, remember, it has to start at maximum displacement. It has to go all the way to the other side and come all the way back to the same point again before one complete oscillation has taken place. Now that's important because it means it passes through the equilibrium position twice in one cycle. which means that if you were considering an energy against time graph, I'm going to draw it like this because the energy never, and this is going to be kinetic energy, for instance. And let's say we start it from maximum displacement. The kinetic energy would be 0. It would curve up, it would curve down, but you would get 2 of these. And that there would be the full time period. That there would be t over 2, which is when it reaches the other side and the kinetic energy goes to 0 again. So please be very, very careful. If they say it's undergoing 3 oscillations, that means it's past equilibrium 6 times, so you get 6 kinetic energy peaks. Super important. And then the final thing that I want to talk about is resonance and forced vibration. So everything we've been talking about here, if I show you this pendulum, is just you displace it and then you release it and it goes on its own. But it is perfectly possible for you to apply a periodic external force to try to force these oscillations. So this would be in the instance of you pushing someone on a swing. You are applying a periodic external force to try and get them to move higher. If the periodic external force has the same frequency as the natural frequency that this thing wants to move in, then you will cause it to go into resonance of maximum amplitude. So again, that's the case of the swing. You push the swing every time it reaches the equilibrium position, which is exactly the right time for it to pick up some speed and go a little bit higher. Because the frequency of your push is the same as the frequency of the swing. So showing you what that graph looks like, if we have a resonant frequency that you are forcing it with, and the amplitude, there's a sort of fixed amplitude, and then it sort of peaks, and then it goes down again. Where this would be the natural frequency F0. So when the applied frequency equals the natural frequency of the system, then it goes into resonance. And you also need to know how damping, I believe, affects resonance. So what happens is, if you increase the damping, you decrease the maximum amplitude, and you actually slightly, I think, is it increase or decrease? It's the same when the damping. So the amplitude decreases more and more. Yeah, it would deviate from F0. I think if we think about this, then if it's heavily damped, it would be slower. So I think the frequency would go down. So it would look something like this. So this would be something like light damping, and this would be something like heavy damping, where the amplitude is lower everywhere, and the frequency, the forcing frequency, would be slightly less because it's just sluggish because it's so heavily resisted, I think. And the final thing I want to go through is a typical question that might combine all of this. So they might say a 0.12 kilogram mass is suspended on a vertical spring and made to resonate by applying a periodic force, an external periodic force, with a frequency of 2.4 hertz. So if it's resonating there, if it's in resonance, then we're assuming that is equal to the natural frequency of the system, which is 1 over t. So the time period is 1 over 2.4, which, by the way, for a mass spring system, would be the 2 pi root m over k that we saw earlier. I'm just going to make sure that I have memorized that correctly. Because for some reason I'm doubting myself. It is 2 pi root m over k, isn't it? And not the other way around. Yeah, perfect. So what we can do here is to work out the spring constant of the system using that, where root k over m is going to be equal to 2 pi times 2.4. So root k over 0.12 equals that, and 2 pi times 2.4, we'll just say that's equal to 24 over 5 lots of pi. We're going to square the answer. So k over 0.12 will equal to 227.4. And so the k is just equal to that times 0.12, which is 27.3. Whoop, that was nearly on the screen, guys. Nearly didn't bomb that. And then the next part of the question, well, actually that, I just wanted to show you that. So it's linking the resonant frequency with the natural frequency of the system, then tying it into the simple harmonic motion stuff that we did before. All right, I think that is a good overview of everything to do with circular motion and simple harmonic motion. As always, if something hasn't been clear, because I know I went through a lot of content there in an hour, so if anything wasn't clear, feel free to drop a comment in the comment section and I'll do my best to reply. As always, I have a Discord server where you can join and drop some suggestions of things you want me to cover. You can also ask any specific questions there. That's a public server. Anyone can join and see what's been going on there. Yeah, always open to suggestions. Do the YouTube-y things if you want this to continue. And I will see you guys hopefully on Monday morning for a live solve of my next physics math paper. Yes, I'll be doing OCRB, the MEI math paper 2 that day. So right, in the meantime, carry on studying. All the best, work hard, and I'll see you then. Take care. Bye-bye.